Hello, Engineer 2202. This is Professor Coates, and we are going to see how this video recording works out. This is my third time doing it, and I'm definitely not a fan, but it is extremely efficient, and hopefully it will be effective. So, last class we spoke about moment of inertia, and recall we said that the moment of inertia was defined by the summation of the product of the individual masses and their distances to a particular axis squared, and that distance was the perpendicular distance from the axis to the mass. Now, we also said that moment of inertia was what? It was a measure of how the mass is distributed about that axis. It's a measure of how the mass is distributed about that axis. And we looked at some cases last time. Now, if we're dealing with a continuous system, a continuous distribution of mass, then that moment of inertia summation becomes an integral. And so this is what it looks like. Of course, it will be the integral of the distance squared. That distance, remember, this is distance from the mass to the axis, and it's a perpendicular to the axis, over dm. Okay, so it's the integral of the distance squared over your elemental mass, dm. So let's look at how we could arrive at the moment of inertia for a slender 1D body. Excuse me. So, in deriving this 1D system, what we're going to do is we'll define an elemental mass dm right here over and with that has an elemental length dr. Okay, so elemental mass dm with a small length dr. So we know since density is mass divided by volume, then we know mass would be density times volume. So if I'm looking at that elemental mass dm, I can say it's going to be the density, rho, multiplied by the volume. Now the volume would of course be the cross-sectional area multiplied by the length. So that's where I get the ADR from. So the ADR term represents an incremental volume. Rho the density and dm the elemental mass. Now if we do that integral of r squared dm, what happens here? If I substitute dm, well, I'm substituting rho ADR for dm in this term here. Substitute rho ADR for dm, I end up with what I have down here. Now if I'm looking at an axis in the center, so if I'm looking at an axis that is perpendicular to the plane of the PowerPoint of the presentation, coming out of the plane or going into the plane, either way it's perpendicular, well, my integral would have to be, my elemental mass would go from either here, this side, all the way to that side, or vice versa. And if we do our typical sort of conventional coordinate system, we're going to end up with what? Start from this side, negative, and go to this side, positive. So if the length of my bar is L, then my limits would be minus L over 2 and L over 2. So here I have my integral. Minus L over 2, rho AR squared. R squared comes from what? Same R squared here. All I'm doing is substituting the dm, or substituting the rho ADR for the dm. So I have rho A here, dr here, that gets substituted for the dm. And then that's a fairly straightforward integral, right? I'm just integrating over the dr, so I have r squared, I end up with r cubed over 3. When I plug in L over 2 and minus L over 2 in my limits, I'm going to end up with something like this. Or not something like this, I'm going to end up with this, right? Recall that mass is density times volume. So for the entire bar, or the whole bar, the entire bar, or mass would be the density multiplied by the volume, A times L, the length of the bar. A is the cross-sectional area, and of course density here is represented by rho. So can we see that if we look here at this rho AL cubed, we could also rewrite it as rho AL times L squared. Rho AL times L squared. Therefore, we can substitute that for that rho AL term. We can substitute M for that rho AL term because we know M is rho AL. So again, if I look here, I can rewrite this as rho AL squared. I'm sorry, rho AL times L squared. So that would just be ML squared. So therefore, I can write my moment of inertia for a slender bar about an axis through the centroid or center of mass as 1/12 mL squared. So we just determined the moment of inertia for a slender bar about an axis through its center of mass, and that slender bar is considered to be a 1D system because essentially one dimension is much more significant than the other two. Now we're looking at a 2D system where we have two dimensions being significant and the third being irrelevant to the problem. So for the 2D system, for the 1D system, what we did was we looked at an elemental mass dm and we looked at the elemental length dr. For the 2D system, we're just going to take it one step, one order of magnitude or 1 degree of freedom more than before. So instead of looking at an elemental length dr, we're looking at an elemental area dA. Okay, so for example, if we have a thin plate, now we're going to define the elemental mass as, we're still using mass equals density times volume, but remember we're using an elemental area now. So when we're defining the elemental mass, we end up with something like this. We end up with the mass dm is equal to rho, the density, multiplied by the volume. But now the volume is going to be that elemental area dA multiplied by its thickness, T. So then we can write moment of inertia, rewrite the moment of inertia. Instead of having the integral of r squared dm, of course, now we're going to substitute the rho t dA for the dm, and we get something like this down here, which would be the integral of rho t r squared dA. Let's check out what this is all about again. Remember, rho is your density, t is just your thickness, and dA is your elemental area. R squared, what was r squared? R was the distance from the axis that we're worried about to the elemental mass, and it was a perpendicular distance. That's very important. Also bear in mind that rho and t can be considered to be constant. We're talking about a thin plate here. The thickness is not variable, same thickness everywhere. Uniform density or homogeneous plate density is the same throughout. So we can take the rho t out because they're constant. We can take them out of the integral, and we end up with the integral of r squared dA. Now that integral r squared dA, that has a name, a separate name as well. That's called the polar moment of inertia of the cross-sectional area. The cross-sectional area. Okay, it's a little bit different because when we looked at moment of inertia, we were looking at a mass distribution. The polar moment of inertia is really about area distribution. Now also keep in mind that rho t, this term rho t, I can replace it by m over a. How is that? We can do that because of this relationship here. Okay, so we know this relationship comes from the fact that density is mass per unit volume. So of course mass is density times volume. So for the entire mass m it must be the density times the entire volume. What would the entire volume be? Well, that has to be the cross-sectional area, the complete cross-sectional area, A multiplied by its thickness. So I know that M is equal to rho T times A. So guess what? Let's come back here. So rho T would have to be M divided by A, right? So that's where this M over A comes from. So finally we can relate the mass moment of inertia of the plate about that z-axis, that axis that's coming out the plane of the board or the presentation here, perpendicular to the plane, to the area moment of inertia or the polar moment of inertia, okay, and by this relationship. Okay, moving on, we can establish another relationship between the moment of inertia about the various axes. Now we're going to look at the moment of inertia about the x-axis, the y-axis, and the z-axis again, and establish a relationship. If I look at the moment of inertia about the x-axis, for example, remember what moment of inertia is now. It's a measure of distribution of the mass. In this case, we're looking at the area we will be looking at the area distribution once I do my substitution here. So I do my substitution as usual. So my dm is what? Rho t dA. Now I have the moment of inertia about the x-axis being the integral of y squared. Why y squared? Why not x squared? Well, remember the definition of the r squared term. For that r squared term, that distance has to be the perpendicular distance from the axis to the point. So what's the perpendicular distance from x to the point where this elemental area is located? It's y, right? So it has to be the moment of inertia of about the x-axis must be the integral of y squared dm. Similarly, the moment of inertia about the y-axis would be the integral of x squared dm. And I do my typical substitution. I'm substituting here rho t dA, rho the density, t the thickness, dA the elemental area. I'm substituting that for my mass dm. Okay, so I have those two expressions. That's fine. Now what about the moment of inertia about the z-axis? Well, it's the usual, the integral of r squared dm. Now my r is the perpendicular distance from the z-axis to the elemental area. Let's go over here. Where's my z-axis? It's coming out the plane. What's the perpendicular distance? Well, it would be this r distance here. Because what? The axis that we're talking about, the z-axis, is perpendicular to the plane of this drawing, is it not? So whatever is in the drawing, that distance from the axis must be the perpendicular distance that we need. But check it out. I know that that perpendicular distance r squared is given by, could be given, or not could be, is definitely given by what, x squared plus y squared. Or I could say we could rewrite it as x squared plus y squared being r squared, right? So if I make that substitution here for r squared, I end up with the integral of x squared plus y squared dA. Guess what? The integral of x squared dA, that's my I sub y. That's the moment of inertia about my y-axis. And similarly, the integral of y squared dA, with the factor rho t, of course, rho times t, is the moment of inertia of about my x-axis. So now I see that the moment of inertia about the z-axis is the sum of the moments of inertia about the x and y axis. Now, clearly the x and y axis are perpendicular to each other. So this is only true for this type of case, where we're talking about two axes that are perpendicular to each other. Then the third axis, the moment of inertia about the third axis perpendicular